I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life, the universe.
Hello, this week we're putting on our swimsuits and diving deep into the choppy waters of the world of vaccines. How do they help us, and why are people becoming so hesitant to get them?
Plus, in the news, a new kind of moonlander, the true cost of streaming videos, and how good are we at spotting postnatal depression in men. I'm Adam Murphy.
I'm Izzy Clark, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
First up, some people call it the organ we overlooked. And it's surprising that we did, given that it weighs as much as your liver and contains more cells and about 20 times as many genes as the whole of the rest of the human body put together. But the importance of the microbiome, the community of trillions of microbes that live on us and in us, is now beginning to be appreciated.
The outstanding problem, though, is that the role it plays in the body in health and disease is very hard to study, because the conditions that support the hundreds of different strains of microbes that live in contact with our own cells are tricky to recreate. Chris Smith spoke with Harvard's Don Ingber, whose team have developed a way to reproduce the microbiome alongside human intestinal cells in long-term culture.
I've been in medicine for many years, and one of the biggest paradigm shifts I've seen over the last 10 years is the discovery that the gut microbiome, the normal microbes that live in our intestines, play a fundamental role in health and disease. And there's really no way to study how they interact with the living cells in our intestine in a simple way. Everything we know about it is based on genetic analysis, which is essentially guilt by association. This bug is there or that bug is not there, in people with different problems or healthy states, but it doesn't show causality.
Why is it difficult then to study how the relationship evolves between host, i.e. us, and microbe?
We don't think about it, but in the center of our intestine, the lumen, oxygen levels are extremely low. And so there are microbes that live in that environment that actually die at higher oxygen levels. Whereas our cells, they need oxygen. And in the body, there's a gradient of oxygen, meaning it's high in the blood vessel and it gets lower and lower as you get farther towards the center of the space of the intestine. And bugs of different types survive in these different regions. So we had to figure out a way to make all that happen by basically mimicking the way it works in our body.
How are you doing this? Is this in a dish?
It's in a device we call a human organ on a chip. These are the size of a computer memory stick. They have two hollow channels, less than a millimeter wide, right next to each other, 2 centimeters in length. The wall between them is porous, meaning things can go back and forth. We literally isolate cells from biopsies from the intestine of human patients, and we culture them on one side of the porous membrane in the first channel. The opposite side, we have blood vessel cells that line the small vessels, capillary blood vessels in our body. By flowing oxygenated fluid or medium through the blood vessel channel, we get a gradient very much like in our bodies, so that there's enough oxygen for the capillary blood vessel cells and intestinal cells to survive. But the oxygen gets so low in the middle of the space above the intestinal cells that we can get all types of bacteria to grow, ones that grow in low oxygen, mid-level oxygen, and higher.
Essentially, then, the oxygen is being delivered by the channel that we're pretending is the blood flow. And it's
exactly like in our body, yes.
Yes, and it's moving across that porous interface between the two channels. It sees the intestinal cells first, so they get first dibs at the oxygen. Some will then make its way into what we're pretending is the inside of the bowel, and that's where you've then got the bacteria growing.
Exactly right. And interestingly, the human intestinal cells spontaneously form these finger-like structures called villi that increase the absorptive surface area of the intestine. And they also put out mucus. And that mucus is a very important boundary between the cells in your gut and the bacteria. And it really is an important part of how they live and grow in our intestine. It's really quite an amazing mimic of how our body is built and how it works.
How do you get the bacteria in, and where do they come from?
We get bacteria from stool specimens from neonates in the neonatal intensive care unit of our children's hospital here in Boston. And there are hundreds of different microbes there, but we're able to keep hundreds of different microbes alive in direct contact with these human cells, that's really is a first.
And what is this going to enable us to do? Now you've got this model system working that we couldn't before.
We're funded by the Gates Foundation to study malnutrition in children in the third world. And there's communities of microbes that actually contribute to the intestinal injury, which is characterized by loss of those finger-like extensions, so less area to absorb nutrients, and a breakdown in the barrier, which actually causes inflammation and injury. We can mimic that by culturing multiple microbes on these chips under similar sort of hypoxia, low oxygen conditions that mimic our intestine.
And what about when we give people doses of antibiotics? Because that's the other issue at the moment, isn't it? We're very worried about antibiotic resistance, but also the knock-on effects through life, especially when you encounter antibiotics at a very young age. Will your system enable us to ask, if I do this, what does it do to the community of microbes that live in the intestine?
It's absolutely true that if you take antibiotics as a child, you can have a long-standing impact on the microbiome. And that is precisely the type of experiment we can carry out. You could look at probiotics people take and see whether they in fact do work. And, we're doing all these types of experiments now.
Gosh, that is some really fascinating work. Don Ingber speaking with Chris Smith there, and the work they were discussing has just come out in the journal Nature Biomedical Engineering.
Now, from stomachs to space, this week Amazon CEO Jeff Bezos has joined that club of moon-sighted billionaires when he revealed his vision, Blue Moon. But is this a proper moonshot or is it something else? Here to chat more about that is angel investor Peter Cowley. So Peter, what has Bezos actually announced here?
Hello, yes, Bezos has announced that he's produced a device or a module which will lift off from the Earth and will land on the moon. So it won't return at the moment, it will just go over there and deliver rovers, it'll deliver satellites, potentially, and instruments. So it's part of his own program, but it's got to the point where he's designed, though not yet launched, a moon lander.
Now, Elon Musk has his fancy big heavy rocket as well. Why is this one different?
Well, there are many, many schools of companies outside governments that are looking at going into space. And the three big ones for the entrepreneurs, as you say, Bezos with Amazon, there's Musk, we know through Tesla and SpaceX, and then Branson with Virgin Galactica. So all of these are sort of competing. There's plenty of other companies doing it as well. And what Musk has said is that I don't know if you were aware, he launched his Roadster, his Tesla Roadster, some months ago into space. Very, very large publicity stunt to some extent. Whereas Bezos is really aiming for the moon. So he has got a different view on this. In both cases, they are entrepreneurs who've made a lot of money and they're funding these space programs. I should point out that Musk has actually got to the point now where they have turnover in the billions and will probably break even, where Bezos is funding it with his own money.
So they're at a very different stage in terms of where they're going.
In terms of size and the amount of funding they have from customers. So Musk has had obviously some external capital to start with and now got a lot of contracts, much bigger organisation. Bezos has claimed that he's putting in $1 billion a year of his own money into this project.
So that means he's got a lot of catching up to do with Blue Moon. So when are they planning to get going?
Well, again, a big difference here. Bezos has only actually sent up 11 rockets so far, whereas Musk has sent up 70-odd, and a lot of successful rockets. In both cases, they've had failures, of course. This is new space, as it's called, rather than old space. And Bezos has said that he should be able to get the device, the launcher up in 2024. Musk has got a reputation for things being late, but I don't think that really matters. These are small companies doing stuff that was generally done by governments and through NASA, for instance.
What chance does this have of succeeding? Is it a pipe dream or?
No, I suspect it will succeed, providing there's enough money to do that. In all cases, what they're doing is taking engineering and money and converting it to something. But bear in mind, well before you two were born, I was in about 12 or 13, man landed on the moon. So, and a lot of things have happened since then in terms of technology and material science, etc. So it's pretty likely that'll happen. What's more interesting, though, is the fact at the moment they're shipping up non-animate objects, i.e. satellites, etc. I noticed when I was doing a bit of research on this that a successful human flight has a 1 in 500 chance of failure. That's still acceptable. If 1 in 500 aircraft crashed every year, that's 80,000 aircraft killing 10 million people. So the safety margins for many people are clearly less, but neither of these entrepreneurs have yet put a human being into beyond a certain distance. Branson's done that, of course, with his module, but the other two haven't.
Is Bezos ever planning to do anything with people, or is he just sticking with big
no,
things?
absolutely. No, they're both Musk and Bezos are planning on doing that.
So what's Bezos hoping to do in the long run with people then?
Well, his idea is to set up a base on the moon. So this, I presume it will be for Amazon Depot, perhaps, or is that too horrible a joke? Musk has also said with SpaceX he would expect to have a base on the moon, but that is the bigger project, which is go further out to Mars. Both are looking at somehow meaning that the human race doesn't have to stay on this planet as we gradually ruin it in the longer term.
It would also mean the competing nations would become SpaceX and Amazon, which is an interesting
Well,
thought.
they still need funding for a lot of places, and the Russian, the Chinese, and the Indians, and the Japanese are all on these paths.
We know he's planning to put the thing into space soon enough. Does he have any visions on when we're going to have a moon base?
No, I've not seen that. But if you take 2024 to go up there, and the fact that once this is only delivering autonomous robots or whatever and materials, I would suspect it's going to take a lot of trips to get the things up there, like dozens, and then it's got to be built. So this is my guess, but I would have thought 2035, 2040 really before we get something where it's human habitable.
So still in the realms of sci-fi a little bit then.
It is. I think I might be dead by then. So. But you two can watch it.
Brilliant. Well, thank you very much for an out-of-this-world interview, Peter.
Thank you very much.
You're listening to The Naked Scientist with me, Izzy Clark, and Adam Murphy. Still to come, how much power are you really using when it comes to streaming videos? But first, depression in the year after having a child is common. Up to 10% of new mothers develop what's referred to as baby blues or postnatal depression. And contrary to prevailing wisdom, it affects men too at roughly the same rates as women.
But a new study from Anglia Ruskin University has found that while the average person is pretty good at spotting when a woman is affected, men aren't so lucky and so are less likely to get help. I spoke to Viren Swamy about what he's found.
Our study looked at how the public understand something like postnatal depression. Specifically, we wanted to know whether the British public would be able to recognise symptoms of postnatal depression when they were presented in the form of a mum having postnatal depression or a dad. So we asked participants from the British public to read a short paragraph that described two cases of postnatal depression. Both cases were identical apart from the gender of the person who was suffering. In one case, it was a dad, and in the other, it was a mum. And we asked them to tell us whether they thought something was wrong with this individual, and if they thought something was wrong, what they thought was wrong. We also then asked participants to rate the cases in terms of how distressing they thought the case was, how sympathetic they thought the case was, how sympathetic they would be to the person, and also whether they would likely suggest that that person got help.
And what did you find? How good were the public?
Well, the public were generally quite good when it came to the female target. When we asked participants whether they thought something was wrong, 97% thought that something was wrong when the target was a woman, but only 75% thought there was something wrong when the target was a man. And of the people who said something was wrong, 90% thought that the woman had postnatal depression, so they were accurate in describing this individual as suffering from postnatal depression. When it was the man who was suffering from postnatal depression, only 46% thought that that person had postnatal depression. Conversely, the public were more likely to think that the man suffering from all these different symptoms was either just too stressed or suffering from a lack of sleep. So they explained it in a non-mental illness form rather than actually identifying correctly that this person had a mental illness.
Why might that be? Why might people be so uninclined to say that about men?
I think there are a number of reasons. Probably one of the biggest reasons is that there remains a myth in society that men can't get postnatal depression, that this is either an issue that only affects mums or women. And specifically, I think that myth comes from this idea that postnatal depression is caused by neurochemical changes that result from pregnancy. And this idea then means that men, because they don't ever get pregnant, means that they can't be susceptible to postnatal depression. And that is a myth. Men undergo all kinds of neurochemical changes as a result of their partner's pregnancy, and that might be a contributor to postnatal depression. I think a second reason why people are less likely to think men can suffer from postnatal depression is because of gender role stereotypes. We are socialized as a society to think that men should be stoic, men should be tough, men should be self-reliant, and mental illnesses are incongruent with our ideas of masculinity. So we don't tend to think of men suffering from a mental illness as being consistent with our ideas of masculinity.
What can we do about this going forward?
I think the most practical thing we can do is to ensure that all parents, irrespective of their gender, are screened for mental illnesses or potential mental illnesses as they become parents. This is really important. Now, how we go about doing that can also be really important, because having conversations with men about their mental illnesses or their mental health symptoms can sometimes be quite tricky, precisely because of their notions of masculinity. They may not be willing to disclose their symptoms or may not be willing to talk openly about their symptoms. So talking about it in a compassionate way, that is really important. Related to that is the real importance of breaking down this myth that men can't get postnatal depression. This is really, really important for two reasons. First, if men don't think they can get postnatal depression, they're not likely to seek help. Similarly, to the extent that health practitioners internalize this idea that men can't get postnatal depression, they may be unlikely to look for symptoms or talk to men about what they're going through. The reality is that a lot of men do suffer and a lot of men are struggling. If we're not getting them optimal health, that can result in horrible outcomes, not just for dads themselves in terms of, for example, suicide, or for the mums in terms of breakdown of the relationship with the dads, but also negative outcomes in terms of the child, whether it's things like the dad not playing or being unwilling to talk or speak positively to the child. There are all kinds of reasons why we need to tackle this issue.
Absolutely. Viren Swamy there. He's from Anglia Ruskin University and his study is in the Journal of Mental Health.
Now, most people are blissfully unaware that whenever they access the internet, they're using a considerable amount of electricity. I would count myself within that number. In fact, the greenhouse gas emissions released to power the internet are greater than the emissions from the entire world airline industry.
It's some scary stuff. Now, according to a new report, this energy consumption is growing alarmingly fast, chiefly owing to one particular behaviour which is eclipsing all other internet traffic: people streaming videos and movies. Ben McAllister has been crunching the numbers.
Information technology is an enormous part of our everyday lives. All the different aspects of IT, devices, data transmission, manufacturing, etc., now comprise roughly 9 to 10% of global electricity demand. When you're using a computer or a smartphone, it can be pretty obvious that you're using electricity. You can see the device, it's on in front of you. However, you might not be aware that if you're accessing the internet, you're also burning a bunch of electricity in other places in the world far removed from your device. When your computer or smart TV is streaming video from the internet, for example, only about half of the total energy consumed goes into the manufacturing and powering of the device. The other half of the electricity is burnt in data centers, buildings full of computers and other devices which store the data that you can access via the internet. When your device accesses that data, the computers in the data center transmit it through the various cables, towers, and networks that comprise the internet. All of that requires electricity. Mike Azas and Kelly Widdicks researched this topic at Lancaster University.
Unlike switching on a light and you can sort of see where energy might be consumed, if you start streaming online video, then that's actually not quite as visible.
Yeah, exactly. And that's what's come up with our studies, really, is that when we talk to our participants about energy consumption associated with their devices, they always think about charging, whereas obviously we're coming from an internet demand perspective.
This invisible energy consumption isn't the same for all devices. Mobile devices, for example, are much more efficient at using energy locally. So when you stream video on your phone, only about 5% of the total energy consumed goes into powering the phone. The rest of it is spent in the data transmission. I've mentioned video streaming specifically, and there's a good reason for that. The latest figures from data providers such as Cisco say that now roughly 70% of all data traffic is video streaming via services such as Netflix and YouTube. When you do the maths and put all of this together to figure out how much of the world's electricity demand is consumed just by video streaming,
it's around 3% of global electricity.
Just in video streaming. And all signs point to that growing over time. The current share of global electricity consumed by IT is about 10%, but projections have that number nearly doubling by 2030.
There's still a lot of room to grow. Digital devices obviously take up a lot of attention and time, but they continually find ways to creep into more areas of everyday life. It's not just the television in the living room anymore. It's the phone in your pocket, the laptop switched on, the home server, the home Wi-Fi router, things like that.
Video streaming has the potential to consume a massive proportion of the world's electricity going forward, and for the most part, it's completely unknown to consumers. Mike and Kelly wanted to look into what was happening on an individual level to drive this massive consumption of data.
We recruited 20 participants across 9 households in the UK, and we carried out qualitative interviews with each of these participants and then deployed routers into their homes which logged all their internet use for a month. And then we conducted extra qualitative interviews with each of the participants after this logging period. And that's when we found that streaming for our households was also a large portion of traffic.
And they found some interesting things about people's video streaming habits.
One thing that doesn't come across in these big statistics, like from Sandvine and Cisco and Ericsson, about the growth of video and things, is what all that streaming is for.
Streaming is becoming the default way to watch television, with more traditional forms of watching such as broadcast access and DVDs becoming more obsolete. Multiple streams are now occurring in the home, with people watching separate content, maybe even in the same room, but streaming separate content away from each other. Also, some of the things that they watch aren't always meaningful in their everyday life, so they might have been watching just to fall asleep or just to kind of create background noise, and this wasn't always creating enjoyment. So the autoplaying of video means people kind of watch more just because the next episode's played, and that kind of puts more strain on the network operators.
And our participants would also point out that they would watch just as a distraction or as trivial entertainment, and that these were from their accounts. And this was particularly common with YouTube.
It looks like, if these 9 households are representative, a large portion of our massive video streaming data consumption could be a result of the multi-streaming and background streaming Mike and Kelly mentioned. They were quick to point out, however, that they weren't trying to blame consumers.
We're not trying to demonize streaming. It's very important to some people, and it will provide accessibility to others.
But they do think that, given so much of this electricity consumption is essentially invisible to the consumer, we should be having an active discussion about it.
I think an important part of this whole debate is about what the internet should really be for. So we could say, streaming is currently around 3% of global electricity, and perhaps that's okay. Video streaming does a lot of good for people, I would say. But should there be an upper bound? So by 2030, streaming could easily be 10% of global electricity. So is that okay? Or is 20% an acceptable limit? It's important to have an open debate about this rather than just let things develop more organically, driven by service providers and in some cases, advertising revenue.
Definitely something to ponder next time you're contemplating watching another YouTube cat video. Ben McAllister there was speaking to Mike Hazas and Kelly Widdicks from the University of Lancaster. And if you'd like to find out more about the news stories we've discussed, the links to each of the reference papers are on our website. That's thenakedscientist.com, along with the transcripts for each interview for every Naked Scientist show.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
You're listening to The Naked Scientists with Izzy Clark and with Adam Murphy. May marks the 223rd anniversary of Edward Jenner's first smallpox vaccine and the 63rd anniversary of the polio vaccine being made available to the British public. So, with a resurgence of diseases like measles around the world, we are looking into the importance of vaccines. First, we're going to jump into the past as we look at the history of vaccines. Smallpox was a disease that killed up to 300 million people in the 20th century. Humans have eradicated it, and that means it's not present on the planet outside specialist labs. And we did that in 1977.
To find out more about how we got into a smallpox-free world, Ruby Osborne took a field trip to visit a herd of cows with Mary Brazelton from the Department of History and Philosophy of Science in Cambridge to learn how Edward Jenner came up with the first vaccine.
We're currently stood in a field with some cows, and the reason that we've come to visit some cows is because they were very important in the development of one of the first vaccines.
That takes us back to the year 1796, and the Gloucestershire physician Edward Jenner, he was actually a country surgeon. People who worked with cows on a regular basis often didn't get smallpox. They would often get cowpox, which is a virus that we now know is part of the pox family of viruses closely related to smallpox that affects cows and that can be transmitted to people when they handle cows quite closely. Jenner conducted a very particular experiment, which is to take an 8-year-old boy by the name of Phipps and introduce cowpox to him through a process that eventually came to be known as vaccination, coming from the Latin word for cow, right, vacca. It's a relatively violent process insofar as you're actually taking a lancet and you're making cuts in the arm or in another part of the body, and then introducing material from cowpox pustules into the body.
And that first introduction of cowpox into the boy was done on the 14th of May, and that's the same date that we are recording this next to these cows.
Then Jenner introduced smallpox to the boy, or exposed him to smallpox, and he didn't get sick. Slowly, over time, it is recognized that using cowpox virus is something that can produce resistance to smallpox. It is also worth noting that there was this older practice of variolation, and was actually quite an old practice, traditionally done in places like the Middle East and China. Variolation or inoculation is different from vaccination because you're protecting somebody against a disease by introducing them to a small amount of the disease itself. Part of the thought was that if you're getting exposed to these things early in life, that's going to give you protection. So the concept of, and some of the practices of vaccination that Jenner was using weren't necessarily so totally new and strange.
And how quickly did the smallpox vaccination catch on? Were people quite accepting of it, or was there any resistance?
Well, there are reports of resistance really that developed quite quickly. Clerical opposition, religious opposition to the notion that by inducing resistance to a disease, you could somehow be subverting divine will. There are concerns about the bestial nature of the process in which you're taking material from an animal originally and introducing it often to the bodies of infants. New questions arise of individual rights and the ways in which individual freedoms might be restricted by larger social mandates to vaccinate for the public good. And some concerns are simply that it will hurt, that it will cause some kind of local reaction, inflammation.
The smallpox vaccine came about really just because of an observation. How did we transition from that to actively trying to develop vaccines to specific diseases?
That generalization of moving from a vaccine for one particular disease, smallpox, to the concept of a vaccine as an intervention that will induce immunity against a particular illness, that is something that we see very much coming out of a much later period, particularly the late 19th century development of things like bacteriology and the germ theory. And so for that, we have to think about really another generation of researchers, people like Louis Pasteur, Robert Koch, and the ways in which they really do several things in rapid succession. They identify particular microbiological agents of disease. And moreover, they seek to develop interventions to develop resistance. So when Pasteur develops a means of making livestock resistant to things like anthrax in the 1880s, he calls that intervention a vaccination in honor of Jenner. And so that's really when we see vaccination emerge as a general term for a variety of immunological interventions, even though many of what we think of now as the fundamental parts of immunology, the fundamental theories and understandings, those come even later. The smallpox virus isn't really even isolated and identified clearly as such until the 1930s with the advent of electron microscopy, because viruses are so small. So all of the work that's done on smallpox vaccination before that is down to empirical work in many ways, which is fascinating, I think.
Ruby Osborne speaking to Mary Brazelton about a very moving issue there. Now, these days, a lot goes into a vaccine, and understanding all the different kinds of vaccines as well as how they work can be a really difficult point to get across. And given the resurgence of diseases that we do have vaccines for, understanding this is more important than ever.
Thankfully, Claire Bryant from the University of Cambridge is here to answer all of our vaccine questions. Hi, Claire. So, to start from the very beginning, what is a vaccine?
So, as we've just heard, a vaccine is a medicine which is designed to train the body to generate a protective immune response against a disease it hasn't seen before. So, it's a medicine that mimics the disease to produce an immune response, but it doesn't make you sick.
Okay, so how does it actually work? How does that give you immunity?
Okay, so to do this, you need to understand exactly what the body does when it sees an infection. And it involves a complex interplay between different series of cells. So there's cells that initially pick up the bacterium or the virus when it comes into the body. These cells will take bits of the pathogen and express it on the surface of the cell. It will also become activated by the infection, and it will move then to the tissues of the body that contain lymph nodes, lymphoid tissues they're called. And in these lymphoid tissues reside other cells. So there are B cells, and what B cells do is produce antibodies, and there are T cells, and T cells are the killer cells that take out infected cells within the body. And so when the white blood cell rocks up with the activated state, with the antigen on its cell surface, it will interact with the B cell. That will cause it to become activated, expand, and produce lots and lots of antibodies, becoming an antibody killing machine. And then the antibody binds to the virus or binds to the bacterium and disables it and kills it. At the same time, it can interact with T cells. The T cells are the sort of killer cells of the body. They will go along and they will take out any cells that are infected. So these two cell populations are really important in generating the response against a pathogen. Now, the point of a vaccine, though, is that it actually needs to work way down the line. So some of the B cells and some of the T cells will actually go into a sort of dormant state. And these cells are then lurking in your body. They are very, very, very specific because they will know exactly what the bug looks like. So next time the bug comes along, or when the proper bug comes along, it will recognize the bug and generate lots and lots and lots of the cells, and that will produce a massive immune response to take out the bug immediately. And you won't know it's going on, hopefully.
Oh, fingers crossed. And is that what we call our immune system memory?
Yeah, that's exactly what immune system memory is. It's the B and the T cells that have been vaccinated for, that are sitting in the body, that recognise that particular bug. So when it appears, they kick off and they're very active and they take out the bug.
Yes, essentially they send in the cavalry.
Indeed, indeed.
But there are different types of vaccines, aren't there? So can you explain how that works?
Yeah, so over the years, the initial types of vaccines, as we heard with respect to smallpox, was what's called an attenuated vaccine. So that is basically the disease in a very low-grade form. So it really is a real live infection, but it's a real live infection that's not very toxic. So you can give that to people. They may get mild sickness, but not very much. It's very safe. But the bug will proliferate and will generate really a pretty natural immune response against it. So they confer the really most specific and usually the longest lasting type of immunity. But we have moved on because the vaccines have to be safe, and this is a real concern. So you can get vaccines that are dead vaccines. So that's where you take the bugs and you kill them. The whooping cough vaccines were made from this. And at this point, you inject lots and lots of dead bugs, and that's your vaccine. And now we become even more sophisticated, so we can take what are called the antigens, so that's proteins from the different pathogens. For example, the tetanus toxoid, one of the toxoid proteins from the toxin, the diphtheria, one of the diphtheria proteins from the diphtheria toxin, or the flu vaccines. The flu vaccines are all based on proteins. And what they are they're proteins that are in the surface of the pathogen. So it's actually tricking the body into thinking that the pathogen's there because you're showing the cell surface protein to the cells.
And why do we have all of these different versions, essentially?
So what we're trying to do, the key thing with a vaccine, is you want to get great immunity, but you don't want to cause any harm to the host because you're choosing to vaccinate healthy people, and what you don't want to do is make those healthy people sick. So the problem with the attenuated vaccines is although they're great, they generate the best sort of immunity, you are actually giving somebody a low dose of the disease, whereas the dead pathogen or the toxoid or the antigen vaccines, they can't cause disease because the pathogen is not able to grow. It's a dead version of the bug. So that's why we developed those, to make it as safe as possible, because that's the whole point. You're vaccinating healthy people and you don't want to make them sick.
Okay, so it's the safest way possible.
Yeah.
Now, how do we protect people who don't have an immune system or they're compromised and they can't get vaccines?
This is the absolute necessity of what's called the herd vaccination, which makes us all sound like a bunch of cows.
As we heard earlier.
And so what that means is that if you can get enough people in the population vaccinated, you can stop the transmission of that pathogen. So measles is a cracking example of this. You need to vaccinate 95% of the people. That means that the pathogen is no longer circulating in the population, which means that immune-compromised people on sort of cancer chemotherapy and so forth, will not be able to pick up the bug because the bug is not actually there because so many people are vaccinated, the bug can't be transmitted anymore.
Now, one thing that I would like to know is why do we need boosters? Sometimes you can have one vaccination and that's all you need. There are a few other examples where you need to come back at later points in life. Why is that?
Depends upon the bug.
Okay.
And depends upon the vaccinations. So live attenuated vaccines are often really good at generating lifelong immunity. Not always, but generally pretty good. With the dead bugs or with the antigen type vaccinations, because they're not totally mimicking the disease, you need to have boosters to keep on boosting your immune system. So some things like tetanus, for example, you need to have every 10 years. And it's just because it's not as efficient as giving a low dose of the disease.
I see. And so how would you know if you needed a booster or your vaccination was doing the job that it should be?
Well, hopefully you won't.
Okay. Yeah, fair enough.
Because if your vaccination is working, then you won't know that you've got the disease. With respect to things that need boosting, if you're on the ball enough, you should know that every 10 years you need to go and get a vaccination. Quite often we forget. But if you're going to different parts of the world where the disease is endemic, when you go to the GP surgery to get your travel vaccinations, then you'll be reminded. If you have an accident in the garden where you cut yourself, for example, you come into contact with soil, you will then think about your tetanus and go and have a booster. These are the sort of routine things that happens. And normally you're not reminded unless you're going somewhere or you go into hospital with an injury or something like that.
And you mentioned a word there that I think is quite important, endemic. So that is something where it's in an area, essentially.
Yeah.
And so what's the difference? Say we talk about eliminated, eradicated.
Yeah.
How do they work?
So eradicated means the disease is not there anymore, and that's smallpox. Okay. Things like measles, we were getting towards being eradicated, but now, because not so many children are being vaccinated, the disease is beginning to come up in the population again, and this is then causing problems. In some parts of the world, they don't actually vaccinate children against diseases. So polio is an example of this in Pakistan, for example. It's a widespread disease in Pakistan because people are not vaccinated against it. So if you go there, you need to make sure your vaccination is up to date for that particular reason.
Claire Bryant, thanks so much for joining us. That's Claire Bryant from the University of Cambridge. As we've mentioned previously, rates of vaccinations around the world have dropped, and this has let diseases like measles, that we've heard about, make a comeback. In 2017, 110,000 people died from measles, most of them children, which is a 22% increase on 2016. And the first 3 months of this year, there was a 300% increase on measles cases compared with the same period from last year.
But why are people turning away from vaccines? And what can we do to best convince them that vaccines are safe? We're joined in the studio by Sander van der Linden. So Sander, why do people have this distrust of vaccines and doctors? Where did it come from?
Well, I think it's really complicated. I think with vaccines, there are several causes. Some are political, so people see it as a threat to their individual freedom. Some are based around religion and values that people carry on within their culture and sort of religious circles. And sometimes people are just confused by misinformation that's being spread on the internet, often deliberately, that causes vaccine hesitancy. So I think it's useful to sort of distinguish between people who are vaccine resistant, and you can think of this as people high on the conspiracy spectrum and totally immune, so to speak, to the idea of vaccines. People who are hesitant about vaccines, who are just on the fence and may have been misinformed, and people who are currently not receiving vaccinations but who might consider doing so. So I think it's useful to try to consider different audiences because it's a complex issue and people have very differing motivations to not get vaccinated or to not trust the medical community.
So there's going to be some people we're going to really struggle to reach and others that we can convince more easily?
Exactly. So if you think about, for example, how people become vaccine hesitant, there's a lot of misinformation on the internet and social media, people hear about in their social circles, and so on. And so that's, those are instances you might be able to correct and intervene. But when you talk about anti-vax communities, so communities that are isolated from the rest of society, that are very difficult to penetrate with factual information or scientific information, communities who've become so entrenched where they're only receiving information from opinion leaders or religious leaders or even, cult leaders, even when you get the facts in, they're not going to do much because people look around and they follow norms and they see what the norm is, and the norm is not to vaccinate. So, research shows it's physically painful for people to deviate from what the norm is often. And so even when, these people are acquainted with the facts, that might just not be enough to convince people. So I think this idea of anti-vaccine communities that are isolated and marginalized are a separate issue from the sort of vaccine hesitancy as a result of misinformation.
Now, with the media and with social media, we see these views all the time. So are they really as widespread as they appear? How widespread are these views?
Well, I think it's difficult to quantify, but vaccine hesitancy is on the rise in most countries, and vaccination rates have dropped in Europe and elsewhere, and that is partly attributed due to vaccine hesitancy. We've seen some instances in the United States, in New York and California, where certainly misinformation has played an important role in fueling this. And to some extent, it's deliberate. So during the presidential election in the United States, there were Russian bots, this was called the Internet Research Agency, who were deliberately starting disinformation campaigns on vaccines, so floating pro and anti-vaccine information to try to get people confused on this very issue. And these were bots retweeting things on the internet. So I think that does play a role in heightening this particular issue. And when people are concerned, uncertain about a variety of things, it's a good moment to try to drive a wedge between a lot of these issues, and not just vaccines, but also other issues people are unsure about, GMOs and things that are related to science and mistrust and so on. So I do think it's on the rise, and that's concerning.
So that makes it even more important to try and change people's minds, but we don't want to do that and make things worse. So how do we debunk these myths effectively?
Yeah, you used an interesting word there, debunk. And so what we've been trying to do is find a new approach, which we call pre-bunking. So we know that debunking isn't as effective just because of the way the human memory works, right? When you've been exposed to a myth, that's what sticks in your memory. And every time you try to debunk it, you repeat it and you correct it. But what people remember is the myth, and they forget about the correction. And so it's very difficult to effectively debunk these sorts of issues. So we try to essentially pre-bunk these things. And surprisingly, or perhaps unsurprisingly, we follow a vaccination metaphor with the idea of pre-bunking. So it's called psychological inoculation. So it works the same way. You expose people to a weakened dose of the myth, of the misinformation, not so strong that you persuade people, weak enough to not overwhelm your sort of psychological immune system, but weak enough that it sounds ridiculous for people, and that you can sort of allow people to build mental antibodies to the misinformation, so that when they're actually exposed to it, they're much more resistant to actually believing it. And we do this in a variety of settings. For example, we've done it in the context of climate change. We do it by exposing the techniques that underlie most misinformation, including vaccines, so things like conspiracies and polarization. And what we do is we preemptively try to acquaint people in a controlled environment with the main techniques that are being used, so that people learn about them. And then when it actually happens, people can hopefully spot the techniques that are being used and recognize misinformation when it's being deployed and be less resistant to it. And we've tried to test that online through a game we've developed, a social impact game, to help to try to educate people and engage audiences, and we found some positive results with that so far. So the idea is to prevent is better than cure, and I think the same is true for misinformation. And if you can get ahead of it, that's better than trying to correct things after the fact.
Now, when we're talking about vaccines, we're talking about children's health. It's a more emotive issue than, say, climate change. Does that change how we have to approach these issues?
Well, certainly. I think what we know from experiments is that if I tell you that vaccines are safe, or if a doctor tells you that vaccines are safe, but then subsequently you come across a picture of the internet of a child, a doctored image of a child that's suffering from a side effect of vaccines, that totally trumps your sense of science and your belief in the scientific consensus. So I think that is an extremely important factor to think about, is that emotions do play a very big role in when people think about their children and putting their children at risk. And I think communicating ways that resonate with people other than just cold facts is what's needed here. So when you talk to parents about vaccines, I think you also have to talk about safety in experiential terms for people and not just facts, because otherwise one side is just relaying sort of cold facts to people and the other side is trying to appeal to people's emotions, and that is an unfair debate.
There's been some talk lately of making vaccines compulsory and undercutting this whole distrust issue. Where do you stand on that? Do you think that's a good idea?
Well, I think it's a really complex idea. I mean, I'm a psychologist, not a politician, of course, but what we do know is that when you start making people do things they don't necessarily want to do or consent to, it can actually backfire and decrease trust and marginalize people further. So I understand there's an important balance here to try to protect people's lives and to save lives and to not let other groups of people put others at risk. But then there's also the very real risk of having people further entrenched in their beliefs, further marginalized in their communities, and lower trust of government further because you're making people do things. So I think maybe one thing to think about is the best way of going about this and how to communicate this and how to get people on board within those communities that will approve to these sort of mandatory plans that are currently being discussed.
Thank you very much for that, Sander. Now, we've still got Claire with us in the studio, so maybe we can put some of Sander's advice to good use. So, Claire, how are vaccine schedules decided?
Okay, so there are three important factors to consider when designing a vaccine schedule, and these are thought about very, very carefully by the companies when they're making the vaccines. So first of all, when you're a child, you're born with antibodies which come from your mother, and they drop over time, so your protection against disease that's conferred by these antibodies begins to disappear. And you need to have got rid of those antibodies in order for your own antibodies to be made in the body. But in order to make your own antibodies, you also need to have your immune system to be competent. So it's a balance between getting rid of the antibodies from the mother and having your own immune system sufficiently active that you can generate your own antibodies. So those two factors are very important. And then the third factor that's really important is when is a child most likely to encounter the disease? In other words, when is the child at most risk? So there's those three factors all calculated in when you're thinking about designing a schedule for vaccination for your children.
We come across combination vaccines. So why are there combo vaccines and how are they tested?
So vaccines are all tested the same way. Okay, it's absolutely critical that a vaccine is safe. And any vaccine that produces really any kind of severe side effect is never taken to market. And also this is tested afterwards. So any vaccines that appear to induce some kind of effects post-marketing and post being released onto the market is actually taken out if there's any kind of severe side effect. So that's the first thing to say. There's a lot of testing involved. Combo vaccines tend to be now vaccines that are important for childhood diseases. So the measles, mumps, rubella, for example, which will contain a mixture of live attenuated vaccines. We know that the children suffer from these diseases at a particular time in their life, all around the same time in your life. So that's when a combo vaccine is produced. And testing schedules over the years have shown that actually you can give a combination of these vaccines together and they don't actually cause any detrimental effects to the children. So you're really being able to immunise against a number of diseases all at the same time, which is the most efficient way to go. It is important to state that when you are testing for vaccines, particularly with combination vaccines or any vaccine actually, but combination vaccines are tested all together. So that's a very, very important part of the safety regime.
And are there side effects to vaccines?
Yeah, there can be side effects to vaccines, and it's specific to each vaccine as to what the side effects can be. So if you're giving an attenuated vaccine, you're giving a low dose of the disease, so you can sometimes get side effects such as fever, which is the common sort of thing you'll get with an infection. Some of the vaccines will have side effects such as sort of a sore arm, which you get sometimes with tetanus. These effects are relatively minor, but they are quite common and they're very well documented. Anything more severe than that takes the vaccine out of the market. But there is one exception to that. So anything that's made in an egg, if you're allergic to egg-derived proteins, then you can have a severe anaphylactic reaction, by which I mean a very severe allergic reaction to vaccines made in eggs. So under those circumstances, those vaccines shouldn't be used in people that are allergic to eggs. But generally, the side effects are really very, very carefully balanced and carefully tested for and considered relatively low grade.
Claire Bryant, thanks very much. You're listening to The Naked Scientist with me, Izzy Clark, and with Adam Murphy. On the way, developing an Ebola vaccine.
So recently a massive outbreak of Ebola swept across West Africa, with cases making as far as the US and the UK. Ebola is a hemorrhagic fever. That means it causes massive bleeding in people struck down with it. And it's part of a family of diseases that came to us from animals like bats. And it includes Ebola virus, Marburg virus and Lassa fever.
Since these diseases often occur in the same place and it's hard to tell which one is which, vaccinating against them can be difficult. That's why a team at Cambridge University are developing a vaccine that will work against all three. Ruby Osborne visited Jonathan Heaney, Professor of Comparative Pathology at the Veterinary School in Cambridge, to learn about the work they've done.
What we've done is develop some new technology that allow us to present the immune system with targets the Achilles heel of these viruses. Our approach is to take these synthetic genes that we've identified that mimic viral proteins and put them into a virus that we know is safe for humans. In that way, it replicates and our immune system is triggered to really start to focus on these proteins by this non-disease-causing viral vector. What we use is a vaccine that was used to eliminate smallpox, and we're able to insert these synthetic genes into the backbone of a smallpox vaccine.
So you take this safe version of smallpox and then you make it present Ebola proteins to the immune system, but it doesn't actually cause the symptoms of Ebola.
That's exactly right. In fact, what it does is trigger the immune system to recognize these proteins in the event that the body comes in contact with the real virus.
How far into the development of this vaccine are you?
We've done significant tests in animals. Don't forget, these viruses are naturally carried by bats and other types of animals in the forest. We use laboratory animals to make sure that these vaccines are completely safe before we get the green light to go ahead and evaluate them in humans. The next step, of course, is then to be able to test them in humans to make sure they're safe. We're now at that stage, and we hope by next summer to be able to start evaluating and testing this in volunteers in England.
So I guess you can test that the vaccine doesn't cause side effects by just giving it to healthy people. But how do you test that it actually gives immunity? I'm assuming you don't give people Ebola and see what happens.
No, we don't. But that's why laboratory animals are absolutely essential. And without laboratory animals, we wouldn't have vaccines. So these animals have been shown to be protected against Ebola and Lassa fever.
You mentioned that these viruses are also in animals. So does that make it more difficult to control them than diseases that are just in humans?
Absolutely. It is very difficult to go out and remove bat populations or the wildlife that carry these. These wildlife are really very common and widely dispersed in West Africa. Hence, it's really almost infeasible to exterminate these animals and to remove them.
Does this mean we're not going to be able to eradicate Ebola in the same way that we have done with smallpox?
It's going to be very, very difficult because there's a natural reservoir. And so really the only best way to deal with this is to vaccinate the populations that are at highest risk.
And the huge Ebola epidemic that we had a few years ago, do we know why it suddenly flared up when it did?
Because it got into large population centers in a place where people had never been exposed before. So they had no prior immunological knowledge. Normally, Ebola flares up in the rainforests of the Democratic Republic of Congo. And these are small, isolated villages. So they can be, if you like, quarantined. And as long as people don't leave those regions while they're alive, the virus or the disease usually just burns itself out. Now, fortunately, in the last 20 or 30 years, we're aware of these epidemics, and there are specially trained healthcare workers that can go out there with all the protective equipment and mobile labs and mobile hospitals and be able to actually help save lives.
You're also working on a project to predict outbreaks and the likely strains that are going to be involved. How do you do that?
So we're funded by the British government now to go into these endemic areas and to trap rodents and other wildlife and to be able to take samples to see what they are carrying, not just the viruses that have infected humans, but to see what else is out there that has the potential to spill over into humans. We sequence these, we accumulate large databases that will inform us about potential threats that are forthcoming in the future.
And then will you be tweaking the vaccine to try and cover those predicted future problems as well?
That's exactly right. We take this information and make sure that our vaccines are future-proofed for future spillovers into humans. This is something that hasn't been done before.
Jonathan Heaney there speaking about his incredibly promising research.
Hello, Chris here. I've just popped in to let you know about something very important, so please listen up. Now, as we approach 2020, we want to put The Naked Scientists on a sound financial footing for that new decade, and we need your help to do it. In fact, we need to raise £50,000, which is about 1/3 of our running costs, and at the moment, we're about 1/3 of the way there. We've managed to do that with the help of less than 1,000 of you, and we're very, very grateful indeed to those of you who have helped. But there are many more of you out there who listen and enjoy the programme every week, and we'd like to appeal to you for your help as well. Maintaining the quality of The Naked Scientists output is very labour intensive, and we do need to pay our hard-working staff who make such a good programme for you every week. So please, do make us a contribution. We've made it very easy to do that. You just go to nakedscientist.com/donate and you can leave us a message. You can also dedicate your donation to somebody if you wish. We'll read those dedications on air, and you can also read what other people are saying too. That's thenakedscientist.com/donate. thenakedscientist.com/donate. We sincerely hope that you can help. Thank you.
And now to finish, it's time for Question of the Week, and Phil Sansom has been sniffing out an answer to this question from Patrick.
My wife wants me to light a candle after doing my number 2 to get rid of the smell. Does this actually do anything? I would love to find out. Thank you.
It's not exactly our first choice of question. On our list, it was number 2. But the Naked Scientists take these things seriously. I will tackle this new frontier in research. I will go out and do a poo myself for science. First, I just need to okay it with the rest of the Naked Scientists team.
No,
of course not.
Gross.
What do they know? My boss, Chris, has the final say.
No, please don't do that, Phil. Please don't do that.
Okay, I guess I need to find another way to answer this question. How about Kit Chapman, the comment editor for the magazine Chemistry World? He can help me out.
Sadly, you can't just burn away the smell of your latest poo. People might think that, based on online videos mixing fire and flatulence, and a quick check produces a whole host of people creating spectacular flames from their farts. This works because hydrogen, hydrogen sulfide, and methane are flammable. But it isn't recommended. You could get seriously hurt, and it doesn't tackle the smell problem. Of the 3 gases, only hydrogen sulfide gives off an odour, and usually that telltale stink from cutting the cheese is caused by a host of other chemicals produced by gut bacteria. It's also important to remember breaking wind provides a relatively high concentration of these flammable gases before they are quickly dispersed in the atmosphere. A good thing too, otherwise a romantic candlelit dinner at a curry house would probably end in 3rd-degree burns. So, a candle flame can't burn off the pong of your number 2. Your toilet deposit isn't a jet of concentrated gas, so it won't cause ignition, and its whiffiness is caused by chemicals that aren't known for spectacular combustion.
Wow, okay, so it's not that simple. The gases that catch fire aren't the same as the chemicals that make the bad smell.
But this doesn't mean Patrick's wife is wrong. If it's a scented candle or a melt, burning it will mask odours and give the bathroom a pleasant aroma. It's because they contain essential oils and other fragrances in their wax. When the candle is burned, the wax melts and the oils evaporate, filling the air with volatile organic compounds, such as limonene, found in citrus fruit scents, linalool in lavender, or pinene in pine. Any of these scents will react with the receptors in your nose, masking the nasty funk from your feces.
But do bear in mind that scented candles have been found to cause indoor air pollution. Especially ones that have paraffin wax, they tend to release carcinogens into the air. And ones that have wicks wrapped around some sort of metal. When you burn them, they can release toxic soot.
So, your choice of candle could make all the difference when it comes to how stinky your toilet seems for the next visitor.
But even if the candle you choose doesn't happen to be scented, the match that you use to light it will be. Or at least it will be for a second. There's a lot of sulfur in matchheads, and when you burn off that sulfur, you make sulfur dioxide. That is a really pungent gas that your nose's smell receptors are particularly sensitive to. Thanks for your help, Kit. You really put us on the scent of the right answer. Now we can flush it from our minds. Next time, we'll be answering this question from Mark.
Is it possible to have so many blood transfusions that your blood type changes?
Thanks, Phil, for nosing around that one for us. If you have a question, you can email chris@thenakedscientist.com, find us on Facebook, tweet @NakedScientists, or join in the debate on the forum, thenakedscientist.com/forum.
And that's all we've got time for this week. Thank you to our guests, Mary Brazelton, Claire Bryant, Sander van der Linden and Jonathan Heaney. And thanks to Ruby for putting the show together. Next week, we're taking to the road quite literally. How do you make a new road and how can we make them greener, cleaner and safer? Do join us then. The Naked Scientist comes to you from Cambridge University and is supported by the EPSRC and Rolls-Royce. I'm Izzy Clark and thank you for listening. Goodbye.